the second fundamental theorem of integral calculus. Okay, so let's move on to the second fundamental theorem of calculus. Now, remember in the previous section, we spent a good amount of time understanding the first fundamental theorem. What did that theorem essentially show us? It demonstrated that differentiation and integration are, in a very real sense, opposite operations, inverse processes of each other. Think of it like this. If you take the integral of a function and then differentiate the result, you get back your original function. Conversely, if you differentiate a function and then integrate the result, you also get back your original function, plus a constant. The first fundamental theorem focused on how differentiation and integration relate. Specifically, it told us that the derivative of an area function gives us the original function. But it didn't necessarily give us a straightforward method for actually calculating definite integrals, the area under a curve between two specific points. That's where the second fundamental theorem of integral calculus, or FTCII as we'll often call it, comes in. This theorem provides us with a powerful and practical way to evaluate definite integrals. Instead of having to go through the somewhat tedious process of calculating the limit of a Riemann sum, which is how we initially defined the definite integral, FTCII allows us to find the area under a curve simply by using the antiderivative of the function. So, we'll be trading in those potentially complicated limits for a much more manageable process of finding an antiderivative and evaluating it at the limits of integration. We'll dive into the specifics of how to do that in the following slides. The theorem statement. Okay, so let's move on to the formal statement of the second fundamental theorem of calculus. As we discussed on the previous slide, the first fundamental theorem showed us the connection between differentiation and integration, how they essentially undo each other. This second theorem builds on that, giving us a method to actually calculate definite integrals. Here we have the theorem stated precisely. It says, if a function f of x is continuous on a closed interval from a to b, and it's important that the function is continuous, we'll touch on that later when we discuss common mistakes, and f of x is any antiderivative of f of x. Now remember, an antiderivative means that if you take the derivative of f of x, you get back to the original function f of x. We write this as f prime of x equals f of x. Then the definite integral of f of x from a to b is given by, and here's the key part, f of x evaluated from a to b, which is equal to f of b minus f of a. Let's break down that notation. The integral symbol, with a at the bottom and b at the top, represents the definite integral of the function f of x with respect to x, evaluated from x equals a to x equals b. The expression f of x, evaluated from a to b, means we take the antiderivative f of x, and evaluate it at the upper limit, b, and the lower limit, a, and finally, we subtract the value of the antiderivative at the lower limit, f of a, from the value at the upper limit, f of b. So, in simpler terms, what does this all mean? It means to find the definite integral, you just need to first find the antiderivative of the function. Second, evaluate that antiderivative at the upper and lower limits of integration. And third, subtract the value at the lower limit from the value at the upper limit. This is a huge simplification. Instead of having to calculate potentially complicated limits of Riemann sums, we can just find an antiderivative and do a little bit of arithmetic. We'll see how this works in practice with some examples on the next few slides, and we'll also cover some common pitfalls to avoid. Conceptual breakdown. Okay, so now let's really break down why the second fundamental theorem of integral calculus works. We've seen the theorem stated on the previous slide, the formula itself, but understanding the concept behind it is crucial. This slide will help us do just that. We're going to look at the process in 3 key steps. First, the antiderivative, which we're calling f of x. Remember, we've been practicing finding antederivatives. That's indefinite integration. What we're doing here is finding a function, f of x, whose derivative is the original function we're integrating, f of x. So, if you take the derivative of f of x, you get back to f of x. It's like reversing the process of differentiation. Next, the evaluation, finding f of b and f of a. Once we have that antiderivative, f of x, we substitute in the limits of integration. B is our upper limit, and O is our lower limit. Think of f of b as the accumulated value of the antiderivative at the endpoint of our interval, and f of a is the accumulated value at the starting point. It's like finding the height of the antiderivative at both ends of the area we're interested in. Finally, the difference, calculating f of b minus f of a. This is where the magic happens. By subtracting the value of the antiderivative at the starting point, f of a, from the value at the endpoint, f of b, we isolate the net change, or the total area between x equals a and x equals b. Essentially, we're finding how much the accumulated value changed over that interval. This difference, f of b minus f of a, is the definite integral. It represents the area under the curve of f of x between those limits. Keep this conceptual understanding in mind as we move on to the next slide, where we'll formalize these steps into a clear, procedural method for solving definite integrals. We'll see how these ideas translate into a step-by-step approach. Procedural steps for evaluation. Okay, so now that we understand what the second fundamental theorem of calculus tells us, that definite integrals can be evaluated using antiderivatives, let's solidify how to actually do it. This slide outlines a clear, step-by-step procedure. Step 1, the very first thing you need to do is carefully identify the function you're integrating. That's your f of x and, crucially, pinpoint the limits of integration. Remember, these are the values a and b that define the interval over which you're finding the area. A represents the lower limit, and b represents the upper limit of integration. It's important to get these straight from the start, as they'll guide the rest of the process. Step 2, next, you need to find the general antiderivative of f of x. We call this f of x. This is essentially reversing the process of differentiation. Remember, we learned about finding antiderivatives when we discussed indefinite integrals. Now, a really important point here. When finding antiderivates for definite integrals, you do not need to include the constant of integration, plus c. Why? Because when you subtract f of a from f of b in the final step, that plus c will always cancel out. So, save yourself a step and leave it off. Step 3, once you have your antiderivative, f of x, you need to write it in what we call evaluation notation. This is just a way of showing that you're going to substitute the limits of integration. We write it like this: bracket f of x bracket closing, with a subscript a and then a superscript b. This notation visually indicates that we're going to evaluate f of x at b and then at a. Step 4, now we substitute the upper limit, b, into the antiderivative f of x. This gives you f of b, which represents the value of the antiderivative at the upper bound of your integration. Step 5, similarly, substitute the lower limit, into the antiderivative f of x. This gives you f of a, the value of the antiderivative at the lower bound. Step 6, finally, and this is the crucial last step, calculate the difference between f of b and f of a. That is, subtract f of a from f of b. This difference, f of b minus f of a, is the value of the definite integral. It represents the net change, or the total accumulated area, under the curve f of x between x equals a and x equals b. We'll see this process in action on the next few slides with some examples, but make sure you have these 6 steps firmly in mind. They're the key to successfully applying the second fundamental theorem of calculus. Illustrative examples. Okay, let's move on to solidifying our understanding of the second fundamental theorem of calculus with some examples. This slide presents our first example, a basic polynomial integration problem. We're asked to evaluate the definite integral of 3x squared plus 2x, with the limits of integration being from 1 to 3. Remember, evaluating a definite integral means finding the numerical value of the area under the curve of the function between those specified limits. Now, let's break down the step-by-step solution. Step 1, find the antiderivative. We need a function, let's call it f of x, whose derivative is 3x squared plus 2x. To do this, we'll use the power rule for integration, which states that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. Applying this to our problem, the integral of 3x squared is 3 times x cubed divided by 3, which simplifies to x cubed. And the integral of 2x is 2 times x squared divided by 2, which simplifies to x squared. Therefore, our antiderivative, f of x, is x cubed plus x squared. Step 2. Apply the limits. Now that we have the antiderivative, we write it in evaluation notation. This means we write f of x with the upper and lower limits of integration indicated like this: bracket x cubed plus x squared bracket from 1 to 3. Step 3. Substitute the upper limit. We now substitute the upper limit, which is 3, into our antiderivative. So f of 3 equals 3 cubed plus 3 squared, which is 27 plus 9, giving us 36. Step 4. Substitute the lower limit. Next, we substitute the lower limit, which is 1, into our antiderivative. So f of 1 equals 1 cubed plus 1 squared, which is 1 plus 1, giving us 2. Step 5. Calculate the difference. Finally, we subtract the value of the antiderivative at the lower limit from the value at the upper limit. That is 36 minus 2, which equals 34. Therefore, the definite integral of 3x squared plus 2x from 1 to 3 is equal to 34. This represents the area under the curve of the function between x equals 1 and x equals 3. Remember, as we discussed on the previous slides, the constant of integration is not needed here because it would cancel out when we subtract f of a from f of b. This example demonstrates the core process of using the second fundamental theorem of calculus to evaluate definite integrals. We'll see another example on the next slide, applying this theorem to a real-world scenario. Illustrative examples. Okay, let's move on to another example, this time showing how the second fundamental theorem of integral calculus can be applied to a real-world problem. This example comes from physics. The scenario presented is: a particle is moving along a straight line, and we know its velocity as a function of time, given by the equation v of t equals 4t cubed, where v is measured in meters per second. Our task is to find the total displacement of this particle between time t equals 1 second and time t equals 2 seconds. Now let's make the conceptual link. Remember from your physics classes, displacement, that is, the change in position, is represented by the definite integral of the velocity function over a given time interval. Mathematically, we write this as displacement equals the integral from t1 to t2 of v of t dt. This is a crucial connection between calculus and physics. Let's now work through the step-by-step solution. Step 1, we set up the definite integral. Based on the problem, this becomes the integral from 1 to 2 of 4t cubed dt. Step 2, we need to find the antiderivative of 4t cubed. Using the power rule for integration, which states that the integral of x to the power of n is x to the power of n plus 1 divided by n plus 1, we find that the antiderivative, which we'll call f of t, is equal to 4 times t to the power of 4 divided by 4, which simplifies to just t to the power of 4. Step 3, now we apply the limits of integration. This means we write the antiderivative in evaluation notation, which looks like this: t to the power of 4 evaluated from 1 to 2. Step 4, we substitute the upper limit, which is t equals 2, into the antiderivative. So f of 2 equals 2 to the power of 4, which is 2 multiplied by itself 4 times, resulting in 16. Step 5, next we substitute the lower limit, which is t equals 1, into the antiderivative. So f of 1 equals 1 to the power of 4, which is simply 1. Step 6, finally, we calculate the difference between the value of the antiderivative at the upper limit and the value at the lower limit. That is 16 minus 1, which equals 15. Therefore, the final answer is: the total displacement of the particle between 1 and 2 seconds is 15 meters. So, you can see how the second fundamental theorem allows us to calculate the displacement directly from the velocity function, without needing to use Riemann sums or limits. This is a powerful tool for solving many problems in physics and other fields. Remember this example as we move forward, as it reinforces the practical application of the theorem. Common mistakes to avoid. Okay, so we've learned how to use the second fundamental theorem of calculus to evaluate definite integrals, and we've even worked through a couple of examples. Now, let's talk about some common pitfalls, the mistakes students often make when applying the theorem. This is really important because avoiding these will save you points on tests and help you build a solid understanding. Let's start with the first, and probably most frequent, error: incorrect order of subtraction. It's surprisingly easy to mix up the order when you're subtracting the values of the antiderivative at the limits of integration. A lot of students will instinctively write f of a minus f of b. Remember, that's incorrect. The correct order is always upper limit minus lower limit. So, it must be f of b minus f of a. Think of it like this. You're finding the change, and you always want the final value minus the initial value. Next up, sign errors with negative limits. This one trips people up too. When your lower limit, which we call a, is a negative number, you need to be extra careful when you evaluate the antiderivative at that point. For example, let's say our antiderivative, f of x, is x squared, and our lower limit, a, is negative 2. When you substitute negative 2 into the function, you get negative 2 squared, which equals 4. Remember, a negative number squared becomes positive. So, when you go to calculate f of b minus f of a, it becomes f of b minus 4. Don't forget to account for that negative sign initially. Now, let's move on to something more conceptual: ignoring continuity. The second fundamental theorem of calculus only works if the function you're integrating, f of x, is continuous on the closed interval from a to b. What does continuous mean? It means you can draw the graph of the function without lifting your pen. If there's a break in the graph, like a vertical asymptote, which is a place where the function goes to infinity, within that interval, you can't directly apply the second FTC. You need to split the integral into pieces around the discontinuity. We'll cover more complex scenarios like that later, but for now, just remember this condition. Finally, confusion with indefinite integrals. This is a really common mistake, especially when you're first learning. Remember that an indefinite integral gives you a family of functions. It includes that plus c constant of integration. But when you're evaluating a definite integral, you're looking for a numerical value, a single number. That means you need to substitute in the upper and lower limits of integration and perform the subtraction. Don't leave your answer as a function of x. It needs to be a constant. So, to recap, keep these 4 things in mind. Upper limit minus lower limit. Watch those signs with negative limits. Ensure your function is continuous, and always simplify to get a numerical answer. Avoiding these common errors will significantly improve your success with the second fundamental theorem of calculus. In the next slide, we'll summarize the key takeaways from this entire section. Key takeaways. Okay, let's recap everything we've learned about the second fundamental theorem of calculus. This is slide 8, and it's all about solidifying the key takeaways. Alright, so the first key point is that the second fundamental theorem of calculus, or FTCII as we've been calling it, fundamentally connects the idea of an antiderivative to the area under a curve. Remember, we started by defining area using Riemann sums, and the first fundamental theorem showed us differentiation and integration were reverse operations. This theorem lets us calculate that area using antiderivatives, which is a much more efficient method. Next, let's look at the formula itself. It states that the definite integral from a to b of a function f of x with respect to x is equal to the antiderivative of f of x, evaluated at b, minus the antiderivative of f of x, evaluated at a. So, we write that as integral from a to b of f of x dx equals f of b minus f of a, where f of x is the antiderivative. Make sure you remember this formula. It's the core of what we've been working on. Now, you might remember from when we learned about indefinite integrals that we always add a constant of integration, c. Well, a really neat thing about definite integrals is that this constant, c, is unnecessary. Why? Because when you evaluate the antiderivative at the upper and lower limits and then subtract, the c terms always cancel out. So, you can safely ignore it when working with definite integrals. Finally, let's break down the process into a simple step-by-step guide. First, you integrate the function to find its antiderivative. Then, you substitute the upper limit of integration into the antiderivative. After that, you substitute the lower limit of integration into the antiderivative. And lastly, you subtract the value you got from the lower limit from the value you got from the upper limit. So it's integrate, substitute upper limit, substitute lower limit, and subtract. If you follow these steps, you'll be able to confidently evaluate definite integrals using the second fundamental theorem of calculus. Now that we've wrapped up the key takeaways, we've covered all the essential aspects of the second fundamental theorem. In the next section, we'll start looking at more complex integration techniques, building on this foundation.